Dear students, now I give the lecture which I should have given yesterday, and I do this now using my iPad. So where did we stop? The idea was to show that Hercules can win again every Hydra. For this, we considered so-called Hydra contexts. This is a set of expressions C such that the placeholder is a Hydra context, and the second clause is if we have a sequence of Hydras and if C is a Hydra context, then the following expression is a Hydra context. So what is the idea? The placeholder marks the rightmost occurrence of a leaf in a Hydra. Now one can show easily by induction on Hydra contexts. If C is a Hydra and if C is a Hydra context, and let's write it like this. And if H is a Hydra, then C, where star is a Hydra, is another Hydra. Now, similarly, we consider ordinal contexts. So first is placeholder is an ordinal context. And second, if alpha 1 to alpha n minus 1 are ordinals denoted by members of E, and if C is an ordinal context, then the following expression, omega to the alpha 1 plus omega to the alpha n plus omega to the C is an ordinal context. Now we get an easy lemma, namely 3.13 lemma. If C is an ordinal context and if alpha is in E, then if we replace the placeholder by alpha, then we get an ordinal in E. Now we can define a mapping, namely we assign to each Hydra context an ordinal context. This is defined in the following way. The ordinal associated ordinal context associated to star is star, and the ordinal context related to Hira context H1 to Hn minus 1, C, is given by omega to the ordinal context associated to H1 plus omega ordinal context associated to Hn minus 1. In fact, here is not the ordinal context, but the Hiras H1 to Hn minus 1, they get associated ordinals. Ordinal associated to H1. And for Hn minus 1, I have the ordinal associated to Hn minus 1 plus, and here comes the assignment of ordinal context to C. Aha. So we get now a mapping from Hira context into ordinal contexts. The next lemma, 3.14, is as follows. If C is an ordinal context, and if you have two ordinals alpha and beta in E, such that alpha is smaller than beta, then C, where I replace star by alpha, is smaller than C, where I replace star by beta. And the proof is easy. Proof by induction on C. And here we using strict monotonicity of the natural sum operation and of ordinal exponentiation. Okay, now we can prove the termination of the Hira method. Let we'll just see that we haven't defined these numbers yet. I have to do it right now. Let O from the Hiras into E be defined as follows. Namely, the ordinal associated to the placeholder is 0. And the ordinal associated to Hira of the form H1 to Hn is omega associated to ordinal, call this O, omega O of H1 plus omega O of Hn. Now we claim that in the Hydra battle, that O of h of I is bigger than O of h of I plus 1. This holds for every step in a Hydra battle. Where hi is a Hydra at time I. Now we have two situations. Assume first that hi has the form, we have some subhydra h prime and a head coming from the root. Then of course O of hi is O of h prime plus 1 bigger than O of h prime, which is the ordinal of hi plus 1. Because if we have here this Hydra, what do? We cut off this head, and then we obtain the Hydra hi plus 1. Now assume that hi is the following shape. It has tree context. And here is a situation where we have a Hydra h prime coming together with a head. And here's h double prime. Now, this has a form. We have a Hydra context C, where this point here is the placeholder. And at this point, we plug in the tree consisting of a root, h prime, and the additional head. And then hi plus 1 has a form C, we have star. And then here we have the Hydra h prime, the head is chopped off, and we have I many copies of h prime. Then O of hi is what? It's ordinal context for C, where I plug in for star the ordinal of the inner hierarchy. Now, what is the ordinal of hi plus 1? It's the ordinal of C, where star is O of this hydra. And now we are done. Because we have that O of this hydra is omega to the O of H prime plus 1, which is bigger than omega to the O of H prime plus omega to the O of H prime, which is the ordinal of this hydra. Okay. So Hercules wins all the time just by using the ordinals. Now the question is, how complicated is the hydra battle? So the goal is now, let us now majorize H epsilon 0 of K by the length of a hydra battle starting with a hydra of complexity linear in K. So we give a hydra basically of complexity K, and then we check how long does it last to kill it. And you'll see epsilon 0 of K as a lower bound. And so this basically shows that the growth rate of hydra battles is as big as this number. And as function of K, this is an unprovable function of Peano-Smithik. So how does this go? Let H of K be the following hydra. Namely, we take a hydra of height K plus 2, and here we have K many direct successors of the root. The idea is then O of H of K will be what? It will be omega an exponential tower of height K plus K. So this is his height K plus 2. And let's see whether this is correct. If we have omega 1, which is omega, this is ordinal associated to the hydra of this form, omega to the 0. So it suffices here to take K plus 1. Anyway, it's not a big deal. So then it should be correct. Let us take this hydra. Now let alpha 0 be the ordinal of h of k, and let alpha I plus 1 be alpha I applied to I. We have now what? Well, what we see here is basically when we look back at the termination proof, then what we see here is basically the ordinal of this one here. Yeah, the ordinal of this one here taken at fundamental sequence I is basically what's coming here. Now there's a small difference, namely here we have I many subhydras. In the fundamental sequence, we have omega to the alpha plus 1 of I is omega to the alpha times I plus 1. So we have to be a bit more careful. So what I'm doing here is maybe it's a bit better to use here I minus 1, where 0 minus 1 is of course 0. Now what's going to happen? H of k has this form. Now first, we calculate the corresponding hydra, and we do k steps in the hydra game, and then these terms will disappear. This means after k steps, we are working on this hydra here. This hydra is omega k. And then we start with omega k, then fundamental sequence at step k plus 1. Let's see. The fundamental sequence is step k. But in the hydra, yeah, we have step k minus 1. So what is going to happen? So first, what do we have? We have, oops, alpha I, well, alpha 0 is basically omega k plus k. It's the ordinal associated to h k. Alpha 1 is omega k plus k minus 1, which is the ordinal h of k. Now this is a hydra at step 0. This is a hydra at step 1. So after k many steps, we get omega k, which is the ordinal associated to this hydra after k many steps. Yeah, now we start at next time is we consider alpha k plus 1, which is omega k of k, and this is the hydra time k plus 1. Aha. So this means we could still use here just I. And then we continue. Alpha k plus 2 is omega k plus 1 will be the ordinal of h of k plus 1. And then now we dropped here some dots. So this is the ordinal of h of k 1, 2, k. And here we have the same. It's the ordinal associated to the hydra k 1, 2, finally k plus 1. And here we have the hydra at time k plus 2. Great. So what do we see? We see that the hydra steps correspond precisely to stepping down the fundamental sequence. Now, the least x less than or equal to k, such that omega kx x plus 1 up to x minus 1 hitting 0 is basically the least m such that h k 1, 2, m it's the body of the hydra. It's just the hydra consisting of one node. Then the node is considered to be dead. So, and this is the same as h epsilon 0 of k. So we see by studying the fundamental sequences and the lengths of stepping down along the fundamental sequences, we can model the stepping down steps in the hydra battle. And we'll see that the hydra battle lasts as long as stepping down along the fundamental sequence. Okay, that was not too difficult, I hope. The question is now, what is the phase transition? So consider a function f. Now consider modified hydras hi of f. And the idea is at time I, the growth rate of new subhydras is given by f of I instead of simply taking I. Now, termination of the modified Hydra battle is the assertion for every H, there's an M such that we start with Hydra H, call it H0F. Then we take the Hydra step at 1, at 2, and finally at argument M. That's not fully true. Instead, we take here not F, but we take here F of 0, F of 1, F of 2, and finally F of M. So, of course, as before, we can show that the ordinal at time I will be bigger than the ordinal at time I plus 1. So, well, now it's a bit difficult in writing down the correct notation. So here I wrote stuff in terms of Hydras, one occurs from the others. And here I wrote Hydra at time I, and here is Hydra at time I plus 1. So to be more consistent, I should write here, I take Hydra at time I and evaluate it. Well, here's f of I, and here's f of I, and I have to do the next step using f of I plus 1. Okay. Now, to make life more easy, we will consider the corresponding stepping down sequence for ordinals. So I start with alpha, evaluated by f of 0. Then I step down in the fundamental sequence at f of 1. The fundamental sequence, I evaluate this at f of 2, f of 3, until f of m. And then it's clear that the descending sequence of ordinals has to stop, which proves termination of the relativized Hydra battle. The question is now, when we vary f, for which functions f does the termination last very long, and for which functions f do we get a shorter Hydra battle, a much shorter Hydra battle. And so what is the goal? If f of I is the logarithm function, binary length function, iterated h epsilon 0 inverse many times, then PA does not prove the termination of the modified Hydra battle. And second, if f of I is similar function, but here we have h alpha inverse of I for some alpha smaller than epsilon 0, then PA does prove the termination. Now we borrow here a result from proof theory, namely that for fixed alpha less than epsilon 0, the totality of H alpha can be proved within Peano arithmetic. And I will reduce this goal to the question how long these descending sequences are, whether they have the growth rate of H epsilon 0 or of some H beta where beta is smaller than epsilon 0. Okay, now it sounds difficult, and it is also difficult. Therefore, we have to consider a technical lemma. So assume that alpha is above 0 and H is a number at least as big as 0. Then, yeah, if you have an omega power of height H alpha plus 1, this allows stepping down along omega H alpha plus omega H. Now this is easy to prove. By induction on H. So if H is 0, omega H, omega 0 of alpha is alpha, and omega L plus 1 of alpha was omega to the omega L of alpha. Now if H is 0, then alpha plus 1 is of course the same as and omega H is omega H of 1. So omega H of alpha is alpha, and omega H is omega 0. It's 1. So this is fine. And second, if H is bigger than 0, then we do the following step. Omega H plus 1 of alpha plus 1 is omega to the omega H of alpha plus 1. Now, by induction hypothesis and the lemmas which we have seen about the stepping down relation, this steps down to omega H of alpha plus omega H. And now we use that omega H steps down along 1 to 1. Okay. This steps down in one step to omega to the omega H of alpha times 2. Which is omega H of alpha plus omega to the omega H of alpha. Now we use that alpha is at least as big as 1. So alpha, therefore, steps down along the fundamental sequence evaluated at 1, also to 1. So this alpha can be modified into 1. So it's omega H of alpha plus omega H of 1, which is the same as omega H of alpha plus omega index omega. Okay, that was not too difficult. Now comes the heart of the argument. Let f of I be, well, I take the logarithm of I h many times. I round up. Now, of course, this could principally become negative, so I guarantee that this is always at least as big as 1, just not to produce too much nonsense. Now, for a given alpha, let beta h of alpha be equal to omega h plus 2 of alpha plus omega h plus 2. Then there exists an I at least as big as h alpha of 1, such that I take beta h of alpha and I step down first along f of 0, then f of 1, f of 2, until f of I. So I will be so big that I don't hit yet 0. But the number of steps is already as big as this number. So this is basically showing that these sequences will become very long. For technical reason, I do an estimate of this. I just want to have that this number is not yet 0. This just shows that the length of stepping down from beta h alpha along f lasts as long as h alpha of 1. This proof is complicated. And this is the heart of the matter, because it basically shows the phase transition for a fixed iterate of binary log function. And next step we make the phase transition depending on h. Proof. Consider the following argument. Beta h of alpha is omega h plus 2 of alpha plus omega h plus 2. Now we step down along 1. We get omega h plus 2 of alpha plus omega h plus 2 of 1. We step down along 1. So what is the strategy here? We don't know yet what these values are. So we just take a lower bound, and this is number 1. So we continue. So what do we do here is we take this number, evaluate it at fundamental sequence at argument 1, and this is the same as taking this ordinal and evaluating this term at argument 1. Yeah, and then we iterate. and iterate. Finally, this term here will become 0. So we get omega h plus 2 of alpha plus 0. Now, how many steps does it require? This requires at least so many steps. M such that, so I have omega h minus 2 plus 2 of 1, 1, 1. So we have stepping down along ones. And this is at least as big as, yeah, we have now this G hierarchy to evaluate this. The Hardy hierarchy was measuring stepping down when these arguments become bigger and bigger and bigger. And when these arguments are constant, then we get here the counting function G omega h plus 2 of 1, which is at least as big as capital G omega h plus 2 of 1. And the G function was working as an homomorphism, from this number to the natural numbers. So this is the same as we take this ordinal and replace omega by argument plus 1. So this will be a tau of 2 right h plus 2. So many steps are required to kill this part here. Okay, that's a preparatory step. Now let alpha 0 be alpha k plus 1 be alpha k of k. So we know that stepping down this sequence to 0 needs as many steps as h alpha of 0. Now what do we claim is we claim that so this is goes in k to alpha k of k in one step. Now that's not what we claim. We know and claim if we take well, that's not correct. Alpha k steps down to this number. So alpha k steps down along k to alpha k plus 1. Now we want to figure out if we have omega h plus 2 of alpha k, and if we have here omega h plus 2 of alpha k plus 1, and we want to step down fundamental sequence at k, how many steps are needed stepping down along k? Well, so how can we describe this? So we count how many steps are needed when we step down at a fixed k plus 1. So this needs ik many steps. So we know that this number steps down along k to this number. So this means it's stepping down along argument k plus 1. Hmm. Yeah, let's see whether this works. So we claim this in, ik at least as big as, now I take a tower of k plus 1s of height h plus 2, many steps. Yeah. That's fine. We know this one. Then, of course, alpha k, all the steps down along k plus 1 to alpha k of k. And so what we see here is this number steps down along k plus 1 to this number. Now the question is, if you put omega powers of alpha k and alpha k plus 1, how much longer will be the stepping down along the same fixed argument? And it will be, the lower bound is a sort of tower function in k. Now, why is this the case? Well, we basically have seen the Stardust induction already, but we just repeat it. So we have omega h plus 2 of alpha k is at least as big as. Now we know alpha k of k plus 1 at least as big as alpha k of k plus 1. This is one of the lemmas which we have seen before. So now we can enlarge this 0 to k plus 1. So we get this at least as big as omega h plus 2 of alpha k plus 1 plus 1. Now this is at least as big as was lemma from before, omega h plus 2 of k plus 1 plus omega h plus 2. Aha, and now comes stepping down along k plus 1. And we repeat this. And at some moment we hit 0 over here. And this uses in, yeah, at least. Then we have ik is counting the number of steps needed here. This is g omega h plus 2 of k plus 1, which is at least as big as capital G of omega h plus 2 of k plus 1, which is a tower of k's of height h plus 2 as a homomorphism law for the slow-growing hierarchy. Okay. Now what do we find in total? We find from omega h plus 2 alpha 0, we get in I1 many steps along number 1 to omega h plus 2 of alpha 1. Then in I2 many steps along number 2, we get to omega h plus 2 of alpha 2. Then we iterate, and along I reach finally omega h plus 1 of alpha k. And doing further, I reach omega h plus 2 of 0. Now, how many steps does this need? Well, all these exponents are at least as big as 1. That's fine. We start with this number, then we get this number, this number, this number, and this is number 0. So the number of steps has a lower bound, the number of steps which are needed such that the sequence of the alpha I hits 0. So you see here the length is at least as big as in at least h alpha 1 many steps. We have here our alpha, which is alpha 0. Then we step up 1, step down. Here we step down at 1, here we step down at 2. Okay. And the length of the stepping down sequences of the alpha i's is given by this Hardy function. Okay. Now we have to show that the indices in the whole sequence are always bounded. Well, these sequences are bounded from above by the corresponding values of the f function. So now let us check that the descent along f from alpha 0 is at least as long as h alpha of 1. Now, this is relying crucially on the following property, which we used before. This uses if gamma steps down along x to delta, and then gamma steps down along y to delta when y is at least as big as x. So we have to show in the whole sequence these numbers showing up here are always bounded by the corresponding counterpart given by the f function. So let I minus 1 be 0. Now going back. So we need here, in stepping down from beta h alpha to this number, this requires so many steps. And let us call this number I1 many steps. So in reaching or in stepping down along fixed number 1, then we have 0 many steps along index 1. So the first stepping down has length I0, and there we only step down the fundamental sequence at argument 1. Now, if we continue further, then we have, well, the next step is we have reached I0, and from I0 we need I0 plus I1 many steps along index 2. And if we are in the transition from index k to k plus 1, we needed I0 plus ik many steps to reach the begin. Stop. To begin, we needed so many steps. And then we added ik many steps along index k plus 1. And in all situations, we have that index IL is at least as big as k plus 1 of height L. So let function g be defined as follows. G of L is k plus 1 for I minus 1 plus I k minus 1 smaller than L, smaller than I minus 1 plus I k minus 1 plus I k. What is going to happen? Then function fl is at least as big as fl at least as big as fik minus 1. Which is at least as big as 2h plus 2. That's this property here. Ik is at least as big as a tower of k's of height h plus 2. So I have here f of tower of height k of height h plus 2. Now this is bigger than f. I take a tower of height h, apply the number k. Now f was a log function iterated h many times. So this is, well, stop. I was a bit too quick. So this is tower of height h plus 2. So this is, now I replace a tower of height h plus 2 by smaller bases in the exponential. Now h was a log function, iterated h many times. Applied to this number. So this is at least as big as 2 to the k, which is bigger than k plus 1, which is g of L. Okay. Now, what's the point? The stepping down, which we did, is we took alpha 0, and then we use stepping down along these indices. This means we step down along function g. We take alpha g of 0, alpha g of 0, g of 1, alpha g of 0, g of 1, g of 2, etc. Now, pointwise, g of L is bounded by f of L. Therefore, the stepping down along g is shorter than stepping down along f. So if you would stepping down along the f function, you got a sequence which is longer than stepping down along the g function, which already uses h alpha of 1 many steps. So let us make this more precise. Let beta 0 of g be beta h alpha, which is beta 0f. Beta I plus 1 g is beta I of g of I. Beta I f I plus 1 is beta I of f of I. Okay, so what is now going on here? This is the sequence which we described. Now stepping down sequence. This is a sequence which we described with the f function. And now we claim beta I f at least as big as beta I j. The stepping down happens at argument I minus 1. And how can we prove this? By induction on I. So if I is 0, there's nothing to prove. Assume that I minus 1 is 0 minus 1 is equal to 0. Well, in the induction step, the two ordinals are just the same. Now assume that beta I of f steps down along gi minus 1, beta I of g. Now the g function is monotone. Therefore, we can replace it here by this gi minus 1 by g of I. Okay, so what does this mean? This means that beta I of f is either equal or bigger. So either we have that this is true, or beta I of f is equal to beta I of g. Then if we add g of I here, it is also true. So this equality in total is true. And then we have here beta I plus 1 of f. Here we have beta I plus 1 of g. Cool. And hence, we see that beta h of alpha, f of 0, f of 1, f of h alpha 1 produces a number which at least is bigger than omega h plus 2 of 0, which is bigger than 0. So this is somehow interesting because this shows the following. So how to think about this? So we have a sequence of ordinals. It's 0. And this requires making these indices bigger at any step. Now, when we use a log function or something like this, then this is not going to happen. Then it could be that we have a moment where these numbers are the same. Now, what we do is we take a sufficiently large omega power such that to kill the new stuff, we could use padding. Namely, we could work for a long time at argument 1 and then going to the next step. And then if you have reached this one, you can step down along number 2 and we are allowed to use however many steps because we have to kill this omega h plus 2 term, etc. So by moving here to exponentials, I induce some more complication into the stepping down process so that I'm allowed to do padding. And the padding is basically coming from the f function, which can be constant for a long time before it starts growing with a plus 1. But this doesn't matter if it's under control. We see that still it requires a long number of steps. So basically, the upshot is conclusion. A does not prove for every alpha there exists k such that alpha f of 0, f of 1, f of k hits 0 if f of I is a function, binary log function iterated h many times applied to A, and then it takes the maximum of both steps. Why is this the case? Because what I can take alpha to be omega, let's say m plus m, then h epsilon 0 of m is less than equal to h alpha of 1. Now, why is this the case? Because h alpha of 1 is h omega m plus m minus 1 of 2, which is h omega m plus m minus 2 of 3, which is basically h omega m of m, which is basically h epsilon 0 of m. Is not fully true because here's not plus 1. So let's take here plus 1, and then it should be fine. Then it's here an m. We get here an m minus 1. And here's m plus 1. Aha, so we have even equality here. So if these numbers are lower bounds for the Hydra battles, then these numbers are lower bounds for the Hydra battles. But these numbers, the function on m, are not truly total in arithmetic. So let us fix the argument. So if PA would prove for all alpha, there exists a case such that alpha f of 0 to f of k hits 0, then PA proves for all alpha h alpha of 1 exists. And then PA proves for all m there's a y h epsilon 0 of m equal y. Because if this is provable, then this is provable, and this is not provable, then contradiction with proof theory. Now we don't do proof theory here, so we have to live with the result that we can prove lower bounds for the Hydra battle with function parameter f using lower bounds in terms of the Hardy functions. Okay. Right. So let us reformulate this. So PA does not prove every Hydra H exists in M such that H f of 0 f m hits 0. And yeah, proof. This uses PA does not prove for alpha there exists M such that alpha f of 0 f of m hits 0. And for every alpha, of course, there exists an Hydra H that the kernel of H is equal to alpha. So if PA would prove termination of the Hydra battle, then PA would prove this one here because any alpha here can be modeled by an Hydra over here. Okay. What is the next goal? Does now prove that for f alpha of I be Aha. Um, okay. 3.17, following lemma. Let f of I be what? Log 2 of h epsilon 0 inverse of I. And let beta be equal to omega m plus 2 of omega m plus omega m plus 2. Then there is number I0 at least as big as h omega m of 1, such that I start with beta evaluated at 0 and at 1, and then at finally at f at I0 I hit omega m plus 2, which is bigger than 0. So it means killing hydras of this form here, hydras having this order notation, killing those ones, even if it's an f hydra with respect to this function, requires so many steps. And this is an unprovable function in M. Okay, now how can we prove this? It's not so difficult any longer. Proof. For I less than equal to h omega m of 1 less than equal to h omega m of m plus 1, which is h epsilon 0 of m. So h epsilon 0 is the same as h e of m, which is h omega m of m plus 1. So epsilon 0 is identified for functional class E. So for all these i's, I make an estimate. Estimate is h epsilon 0 inverse of I is less than equal to h epsilon 0 inverse of, yeah, it's less than equal to m. And then fi is at least as big as function fm of I, which is defined as log 2m of I. Well, yeah, I also use basically that take here the maximum number and 1, and fm is this function, is the maximum, the number and 1. Aha. Now by lemma 3.16 we find that beta f of 0, beta fm of 0, beta fm of 1, fm at h omega m of 1 least as big as omega m plus 2 bigger than 0. Now we claim can replace here the fm's by f. Claim is beta f0 f of h omega m of 0 is bigger than h omega n plus 2 bigger than 0. Okay, how can we prove this? Well, proof. Let beta minus 1 f be equal to beta and beta I f equal to beta I minus 1 f of I. Claim where we form the corresponding numbers beta minus 1 fm is beta, beta I fm is beta I minus, have to be careful, here is an f involved, and here is fm involved. The claim is what beta I of fm is less than equal to beta with respect to index fmi to beta I of f. Prove this by induction on I. If I is 0, then we are done because we start here with the same numbers. Now assume beta I of f is less than equal to fm of I, beta I of f. Here's beta I of fm. Now what we know is that we can replace here I by I plus 1. This requires fm is weakly monotone and the properties of fundamental sequences. Now this means beta I of f, and here I can take beta I m, beta I f m of f m I plus 1 is less than equal to this number. By an argument which we have seen before. So this is clear if both numbers are the same. If they're not the same, take this number and can step down along this number, and we do not, and we possibly hit this number, or we are staying above. But anyway, using this index, we can step down from here to here. So this number will be bigger than this number, and therefore this number will be bigger than this number. So we get this inequality. Now we use here that f of I plus 1 is bigger than this number here. Note, this does not require monotonicity of f. And this steps down along fm I plus 1. This is fine because in stepping down the fundamental sequence, we can make the arguments bigger here and can use the Bachmann property. And this is finally beta I plus 1 of f. So that's great. So we have proved our claim. Stepping down here needs at least as big as so many steps as before. And yeah, yes, and a 1. Okay. Now, same consequence as before. Namely, if f is the maximum of 1 and log 2 h epsilon 0 inverse of I, log 2, let's say, rounded upwards, then the A does not prove for all hydras H. There is an M such that if I take H, now with respect to function f, I take it at 1. That I hit the hydra without any head. And okay, how can we prove this one? Well, let H be the following hydra. We have a linear hydra. And we have to figure out how to model omega m plus 2 of omega m. This is omega m plus 2. So we need here height m plus 3. And here's another one which we need of height m plus 3. And then ordinal associated to H is omega m plus 2 plus omega m plus 2. And killing H requires H omega m many steps, at least. And now H omega m plus m of 1 is at least as big as H omega m of m plus 1, which is H epsilon 0 of m. And we know H epsilon 0 is not provably total in PA. And since we do not prove 0, we just happy with the result that H epsilon 0 is a lower bound for these hydroballids. Okay. And what's going to happen next? Next, we study the provable versions. But first, I do a break. Dear students, I now continue with the lecture. And so what is the next goal? We fix f alpha of I to be equal to log 2 h alpha inverse of I. Then somehow we take the integer part. And again, we take the maximum of this function in number 1. And then we basically show that for all k, there's an m bounded by h omega to the alpha plus 4 of k, such that if we start with omega k, f alpha 0, then consider this as f at alpha 1, and we take fundamental sequence along f alpha, then we hit 0. And what's important here is that for input k, starting with hydra of height k, there's an m bounded as a function on k, and the bound is given by some h beta of k, where beta is smaller than, well, beta is a fixed element in E, so alpha is smaller than epsilon 0. Now, how can we prove this? For this, we use a different technique. So we begin with recalling some basic definition. So let m0 of x be equal to x, and ml plus 1 of x equal to m to the ml of x. Further, let 2n be 2n of 1, which is a tower of 2's of height n. First lemma, 3.18, is as follows, namely, it looks a bit counterintuitive. So we take 2n, and now we take a tower of height k applied to n. Now, at first sight, you would conjecture that this is a tower of 2's of height 2 to the n times k, but this is wrong. This is bounded by 2 index n plus 2k minus 1 for nk bigger than 0. The reason for this is that first you build a tower of height n. On that, you build a tower of height n. On that, you build a tower of height n. But it's different from taking a tower of height 2 index 2 tower of 2's of height n times k, because when you put a tower of height n on top, put a tower of height n on top of a tower of height n, then you have to apply the rule a to the b to the c is a to the b times c. So the complexity drops in a multiplication. Now, therefore, we can prove this as a simple induction. So everybody will be able to show this. It's induction on k. K equals to 1. Or left-hand side, we have 2nk, k equal to 1. This is okay. This is 2n. And on the right-hand side, we have 2 to the k minus 1. Well, what do we have here? 2 index n plus k minus 1. Bounded by 2n plus 2k minus 1. So everything is fine. So the assertion holds. Now assume k is bigger than 0. And assume induction hypothesis. Assume result for k. Then we have 2 index n. K plus 1 of 1 is 2 index n to the 2 index n of k of 1 bounded by 2 index n to the 2n plus 2k minus 1. Now, what is this? This is the same as 2 to the 2n minus 1 to the 2n plus 2k minus 1. The same as 2n minus 1 times 2n plus 2k minus 1. So what you see here is a multiplication effect. So this is bounded by 2 to the 2n minus 2 plus yeah, we write this here as an exponential of 2's. So we obtain here 2n minus 2, 2n minus 1 plus 2k minus 1. Bounded by two to the 2. Now we have is a sum, and 2 to the x plus 2 to the x is bounded by 2 to the x plus 1. So that's fine. So what I'm doing here, Mm. So n is bigger than 1. Well, n is bigger than 0. Now here I make an estimate in n minus 2. So let's assume n is at least as big as 2. Then we continue here. And then we use what I just said, namely this term here is strictly smaller than this term, because n is bigger than 1. This term here, so this term here is also strictly bounded by this term here. So in total, we can bound this term plus this term bound by this term. That's fine. And this in total is what? This is nothing else than 2 to the n plus 2k. Aha. So this minus 1 goes with this 2. This 2 times k minus 1 goes with these 2's. And we are done. So we are left with case n is equal to 1. What we then have to show is that 2k, so n is equal to 1, 2k1, which is 2k, has to be less than equal to 2 index 2k minus 1. So n is equal to 1. So 2 times k minus 1 is fine. And we see that this is true because k is bigger than 0. So this is sort of a trivial exercise, but we have to know it, so to say. Now comes next lemma. .19 lemma. Let alpha be at least as big as omega to the 4. And have alpha of I be equal to log 2 h alpha inverse of I. Now I avoid mentioning the maximum, or maybe I write it down. And then there's one problem. The problem which we want to discuss is this function f alpha is monotone as a function of log, but it's anti-monotone in the inverse Hardy function. So we cannot simply say that f alpha of I is less than equal to f alpha of I plus 1. If we can compensate for this by just estimating it, f alpha of I is bounded by log 2 L of 2 to the h alpha of L for all I less than equal to 2 to the h alpha of L. Now, what is the basic picture? The log function is increasing. At some moment it drops down, and it will become increasing again. Some moment it will drop down. And of course, it is not monotone in these regions here. The trick is now, what we do is we go with the rightmost endpoint to maybe to a point like this. And this point here is bigger than this point, bigger than this point. Here on this interval it's monotone, on these intervals it's monotone, that's all fine. And by going with this point far enough to the right, you can guarantee that we have sort of monotonicity. Now this is sort of a nuisance, but we just do so. So, proof. For an interval of the form, for I in the interval of the form H alpha of L until H alpha L plus 1 minus 1, we have that's inverse Hardy function, E its value A. And so for this interval, you have that the F alpha function is constant. No, F alpha function is monotone. If alpha I is log L of I, L is constant. And this is bounded by log L of 2 to the H alpha of L. Okay, so we have covered basically this part here. Now we have to guarantee that this point here is far enough to the right to materialize this point. Well, we have F alpha of H alpha L minus 1. So we are basically at such a point. This is basically log, there's one iteration less. And now we make a slight estimate. And now we remember that the Hardy function H omega to the alpha, well, H omega to the H omega of x is basically 2 times x. H omega square of x is basically exponential function in x. And you have here, now we make an estimate. We have alpha is omega, at least omega to the 4. So this function is growing faster than the tower function. So this is bounded by log L of 2 to the H alpha of L. So by making this number bigger into exponential, this is replaced by seeing here replacing here L by L minus 1 by L. Actually, this nothing is needed because you have just here the exponential function. So we don't even need further estimates. So this is just true because 2 to the H alpha of L is an exponential function and compensates for one logarithm. Okay. Now assume, oops. Assume what? Assume now that I is less than equal to some H alpha K minus 1 with K being minimal. And find R such that K plus R is equal to L. So K will be bounded by L, and so we find an R non-negative, such that K plus R is equal to L. Then we have, this is K, H alpha of K minus 1 less than equal to I less than equal to H alpha of K minus 1. Because the Hardy function is strictly monotone. Then we have what? If alpha of I is bounded by the argument you have just seen by log 2, K minus 1, H alpha of K minus 1, bounded by log 2 of K of 2 to the H alpha of K, bounded. And now we iterate this log 2 of K plus R. And here we take a tower of 2's of height R. H alpha of L of, now this is K. Now, and then we claim that this is bounded by log 2 of L, so K plus R is L, that's fine. And here we have 2 to the H alpha of L. Why is this the case? Because this H alpha of K will be much smaller than H alpha of L, because alpha is big. So therefore, H alpha of L will be bigger than power of 2's of height R, H alpha L minus R. Because if alpha is at least as big as this number, H alpha will be growing faster than the tower function, and therefore because H alpha of K plus P plus 1 will be at least as big as exponential of H alpha of K plus P. Okay. That's fine. Because we need this lemma for technical reasons. There's another lemma which we need. So this was lemma 3.19. Now comes 3.20. The number of beta less than alpha, such as the maximal coefficient of beta is bounded by x, is bounded by g alpha of x. So what is g alpha of x? G0 of x was 0. G alpha plus 1 of x was 1 plus g alpha of x, and g lambda of x was 1 plus g lambda at argument x of x. What do we know? We know g lambda of x and we know that g lambda of x is bounded by g lambda of x plus 1. This is proved in the same way as if you would show that previously defined function h alpha of x is bounded by h alpha of x plus 1. So the estimates we did before were showing that there is a close connection if we have a capital G function or a small letter G function. So what was the characteristic definition of G? G0 of x was 0. G alpha plus 1 of x was 1 plus G alpha of x, and G lambda of x was G lambda x of x. So what is the difference The difference is this +1 in the limit case, which doesn't exist over here. And this causes a slight change. Just the +1 in the argument compensates for this. So if you do the estimates for comparing functions, then we can just easily verify this. Now, using this material, we show the claim by induction on alpha. So if alpha is 0, left in this set will be empty, and G0 is 0. That's fine. Now, if we have the number of beta less than, if you have a successor number, of course, this is the same as the number of beta less than gamma, such that the maximal coefficient of beta is less than or equal to x, +1 less than or equal to, because it could be that gamma is in this set, but it's not in this set. So the only additional element which could be in this set would be gamma. Therefore, this number is bounded by this number. Now, by induction hypothesis, this is bounded by G alpha, G gamma of x +1, which is G alpha of x. Now, if alpha is a limit, then beta smaller than alpha and maximal coefficient of beta bounded by alpha implies now that it's x, of course, is equal to x. This implies that beta is bounded by alpha x. This is one of the lemmas which we have seen before. Therefore, the number of beta less than alpha, maximum coefficient of beta is bounded by x, is bounded by the number of beta smaller than alpha x, maximum coefficient of beta is bounded by x, +1. Because the only missing element actually there's no missing element. So if beta is smaller than alpha, maximum beta is beta less than or equal to x, then we have this property. Actually, these numbers are the same, but it doesn't matter. We can do an estimate. And then we get here G alpha x +1, which is G alpha of x. Actually, it seems that we could work directly with this function, but doesn't matter. So we have this bound, bounded by G alpha of x +1. And what I just see here is we could even replace the alpha x +1 by the alpha of x. But this is not important for the overall argument. Okay, now comes the magic. 3.20 theorem. Again, let alpha be at least as big as omega to the 4. F alpha was log 2 of h alpha inverse of I, apply to I, and then rounded maximum number and 1. And then we can show the given k, the least m such that omega k of f alpha of 0, f alpha of 1, f alpha of m, it's 0, is bound by 2h alpha h omega to the alpha +1 times 4 of k. Aha, so I think I have now to correct me. Previously, I was just claiming that this number was sufficient for bounding it, but now I make the number slightly bigger. But the proof will show that the original bound will still be fine. Anyway, this is also fine, a fine number. What is important here? The importance here is, so this is bounded by 2h omega alpha plus 1 times 5 of k, bounded by h omega alpha plus 1 times 6 of k. So there will be a fixed number smaller than epsilon 0, so an element in E, such that this least m as a function on k is bounded by a function of that form. Okay, now how can we prove this? And that's a tricky proof. So let gamma 0 be equal to omega k, and gamma I plus 1 is gamma I of f alpha of I, for I less than equal to n. So what's going to happen? Well, recall the following: the maximal coefficient of alpha I is bounded by the maximal coefficient of alpha and I plus 1. I guess that I've shown it. If not, this is proved by induction on alpha. Now, why is this the case? The maximal coefficient counts the maximal natural number showing up in I have to be a bit more careful in writing. I have to write here the maximum. What's the maximal coefficient of alpha and I plus 1? Well, if I look into alpha, the maximal coefficient of alpha I appears by we take something out of alpha, doesn't make the maximal coefficient larger, and there will be some new maximal coefficient, namely the number of new sub-expressions showing up by defining the fundamental sequence. The number of new sub-expressions is I plus 1. So that's great. Then we see that for all I less than equal to m, the maximal coefficient of alpha I is bounded by, the maximal coefficient of alpha I is iteratively bounded by the maximum taken over j less than equal to I, f alpha j plus 1. So why is this the case? Yeah, well, we prove this by induction on I. I have to be a bit more careful, namely the alpha I is in the meantime a gamma of I. Yeah, well, we can just see it. We start with gamma 0. Gamma 0, and we have here f alpha of 0, gamma 0, f alpha of 0, f alpha of 1. And then we see the maximal coefficient of such a term is given by the maximal coefficient of the latest element plus the maximal coefficient of the previous stuff. The previous stuff, we form a maximum for j smaller than I, and then we take into account the last term showing up over here. And we have to be careful, the maximal coefficient, where here is I, is bounded by the number plus 1. Well, of course, morally, we want to have that this should be the same as f alpha I plus 1. But this is not always true, because the function f alpha can sometimes jump in the wrong direction, because have the log function iterated Hardy function inverse many times, and every now and then the Hardy function, inverse Hardy function makes a jump, and then the numbers become smaller. But anyway, this is of course a basic idea. The rest is making just a bit more noise in the construction. So this is the basic pattern. Okay. Now, so what did we just show? We showed maximal coefficient of gamma I is bounded by the maximum taken over j less than equal to I if alpha j plus 1. Now, what do we know about these terms here? Well, we know what 2 to the h alpha of h omega to the alpha plus 1 times 4 of k is bounded by, well, from an exponential, we now go to Tower function, so making the number much, much bigger. Now, the h alpha function, alpha is at least as big as omega to the 4. So the 2x function is bounded by h alpha, let's say. Well, for level 2, h omega square was the exponential function. H omega 3 is a tower function, and h omega 4 is the iterate of the tower function. So what does this mean? This means that 2 index h alpha of x is still bounded by h alpha of x plus 1. Therefore, you can bound this term by h alpha of h omega to the alpha plus 1 times 4 of k plus 1 minus 1. Well, here is even strict smaller. Okay, and now we can use the estimate about the f alpha function, which we have seen before, in intervals of this form. The f alpha function is constant. So the f alpha function is given by the value. Well, what does this mean? Well, we can now show for I equal to m, we have f alpha I is bounded by f alpha of the m is in the meter. This is somewhere here in the middle. But so the m is bounded by this term. But here we have a 2 index function. We have even bound by this function. So this is our M. So for I less than or equal to M, f alpha of I is, now we have to look back. This estimate for I here, we have that f alpha of I is log L of the rightmost term. Right. So I is in this interval, but you also have I is less than or equal to 2 to the h alpha of L. So we can estimate the term by log of L of 2 to the rightmost endpoint. That is what we do here. We take f alpha I and then 2 to the rightmost endpoint. So we can plug in here f alpha of M. So we can assume basically that we have monotonicity here. That follows by the lemma before. Okay. So we have this bound. So this is important. So M is chosen such that for I less than or equal to M, f alpha of I is less than or equal to f alpha of M. Now this whole argument does not really depend on a specific choice of M. The only important point is that we have to go with M far enough to the right so that the function value here is bigger than all the jump points to the left. Okay, what do we have now? We have a sequence gamma I. We have gamma 0 bigger than gamma 1, bigger than gamma f alpha of M. Moreover, we have that maximal coefficient of gamma I is bounded by f alpha of M. That follows from this observation. Now we have found a sequence of M plus 1 many terms having these properties and they are below this number. Actually, this is omega k. So we have M many terms. Okay, this is fine too. M is bounded by the number of alpha smaller than omega k, such that the maximal coefficient of alpha is bounded by, alpha is not so good. Take here gamma. Maximal coefficient of gamma is bounded by f alpha of M plus, now what? The maximal coefficient actually here was not bounded by f alpha of m, but by f alpha of m plus 1. Where was it? It was this estimate. So I have to use here f alpha m plus 1. So this maximum coefficient is what? Is bounded by, strictly bounded by taking this number plus 2. Aha. Now we use the lemma we have proved before, namely this one. So we bound this one here by, we take this I think we better use here less than equal 2 and here plus 1. So what was the lemma? Yeah, so this one here was bounded by g alpha of x, strictly bounded, or is equal to g alpha of x plus 1. So we have to calculate g omega k of f alpha of m plus 1 plus 1, which is what? The g function was a homomorphism from ordinals to natural numbers. So we take f alpha m plus 2, form a tower of height k, and apply this to number 1. Aha. Now we plug this into the definitions. So what do we obtain? You take here log 2 of h alpha inverse of 2h alpha, where beta is now omega to the alpha plus 1 times 4. So we have h alpha of h beta of k of 2h alpha h beta of k. Now we make an estimate, makes the number bigger by deleting the 2 over here. And then we have h alpha inverse of h alpha, so this is bounded by log 2 of h beta of k. And here we have 2h alpha h beta of k. Now here's a tower of 2's of this height, and here's the log function applied so often. So this is bounded by 2 index h alpha h beta of k minus h beta of k. This k times iterated applied to 1. So it's a messy term. But now we take our lemma from before, the lemma about iterating these towers of 2's. And what do we obtain? We obtain here a bound of the form 2 index h alpha h beta of k minus h beta of k plus 2 times k minus 1. Now, this is smaller than 2 index h alpha h beta of k, which is m. This will be a contradiction. M is strictly smaller than m. That's not possible. Now, why is this smaller than this? Well, you have to show that this is the same. So you have to show that this is negative. So minus h beta of k plus 2 times k minus 1 has to be smaller than 0. But this is obvious because beta is bigger than omega to the alpha plus 1 times 4. So this function here grows much faster than an exponential function in k. And this is a linear function in k. So we are done. So that was a magical proof. And I hope that you enjoyed it. And maybe I stop for now. And I will continue next time with phase transitions for Gustin sequences.